Welcome back to the course on machine learning with Python 3. This is Model 3, Classification Part 1. The course is given by Subaraj Academy. We are at Lesson 3 of Classification, which is Support Vector Machine. The Lesson 1 was Logistic Regression, and Lesson 2 was naive Bayes. Lesson 3 Support Vector Machine is one of the important topics of classification. So when it comes to support vector machine, you should know what is hyperplane. Hyperplane is a flat subspace of one dimension less than the space it resides in. For instance, if it is residing in 3-dimensional, then the hyperplane will be 2-dimensional. If it is residing in 2-dimension, then the hyperplane will be 1-dimensional. And the hyperplane is a plane that divides the n-dimensional space into two separate regions. Let's consider 2-dimensional space, which is a plane, not like rectangle or square. In this case, hyperplane would be a straight line because dimension 1. That will divide the plane into two halves. One half lies on one side of the line and the other half on the other side of the line. Understood? So we'll be more interested in 2-dimensional space. So we'll draw a hyperplane, which is a line that will divide the space into two parts, one above, one below. Okay. In 3-dimensional space, hyperplane is a 2-dimensional subspace. It can visualize as a plane that separates the space into two distinct regions. Like, you can have a rectangle which divides the 3-dimensional space into 2-dimensional spaces. Imagine a sheet of paper floating in 3-dimensional space. This paper represents hyperplane. So that divides the surrounding space into two parts. So we are interested only in 2-dimensional space. Now beyond 3, it will be difficult for you to imagine. So the general equation of a hyperplane in n-dimensional space can be defined as a1x1 plus a2x2, etc. up to an xn plus b, a constant, is equal to 0. So where a1, a2, etc. up to an are coefficients associated with the coordinates x1 to xn, and b is a constant term. Okay, this is an equation for the n-dimensional space. In the context of machine learning and support vector machine, a hyperplane is used to separate data points of different classes. For instance, a customer bought a car or not. There are two different classes. To separate them, see, all those who bought the class on one side of the hyperplane, all those who didn't buy the car is on the other side of the hyperplane. In the binary classification we are talking about, the hyperplane acts as a decision boundary that divides the feature space into two regions. One corresponds to each class. Class is nothing but those customers who bought the car and those customers who didn't buy the car. Okay? Or if you take the Harry data set, it will be, of course, there will be three classes. If you take about customer churning, customers who are churned and customers who are not churned are two classes. The goal of support vector machine is to find an optimal hyperplane that maximizes the margin between the classes. If you're talking about binary classification, the margin between the two classes, yes or no. So if it's higher, it's better, so that you'll have lesser error. So that margin is nothing but the distance between the hyperplane and the nearest data point from each class. It's important to note the hyperplane does not always have to be linear. Of course, now in this lesson we'll talk about linear kernels, linear hyperplane. And in SVM, the use of kernel functions allows to for nonlinear decision boundaries, which we are going to talk in the next lesson. So both linear hyperplane and nonlinear hyperplane will be addressing in the support vector machine topic. So this lesson is dedicated to linear hyperplane. What is the decision boundary? Hyperplanes are decision boundaries that help to classify the data points. You understood, I think. So those who bought the car, one class, and those ridden by the car is another class. The hyperplane separated into two. That is called decision boundary. Data points falling on either side of the hyperplane can be attributed to different classes. Also, the dimension of the hyperplane depends upon the number of features. The number of input features is 2, then the hyperplane is just a line. I would say number of output features, not input features. Input feature can't be anything. Number of output features are response variable is 2, then the hyperplane is just a line. In the three-dimensional space, hyperplane is a flat affine subspace, dimension p minus 1. In three dimensions, the hyperplane is a flat two-dimensional subspace. If p is equal to greater than 3 dimensions, it can be hard to visualize a hyperplane. It will be there, but you can't visualize it. But the notion of p minus 1 dimensional flat subspace still applies. In two dimensions, a hyperplane is defined by the equation beta naught up to beta p xp plus b is equal to 0. It is the equation of the hyperplane. If a point x, the predictor or the feature or independent variable is x1 etc. of the xp, the transpose t in a p-dimensional space with a vector of length p satisfies the previous equation. The next lies in the hyperplane. If it is equal to 0, then x lies in this plane. If it is greater than 0, if this equation, when we sum it, if it is greater than 0, then it lies above. If it is less than 0, it lies below. So we can think of a hyperplane as a dividing p-dimensional space into two halves. One can easily determine on which side of the hyperplane the point lies by simply calculating the sign of the left-hand side of the equation. So if it is less than 0, negative on one side, and greater than 0 on the other side. If it is equal to 0, then the point lies exactly on the hyperplane. So look at some examples. So it's a two-dimensional space, a line. So these are two classes. Maybe those who bought the car, those ridden by the car. Suppose the three-dimensional space, then you have a flat surface. A tennis example. So you look at the temperature and humidity. These are two features or two independent variables. And this hyperplane. On one side of this, they will play tennis, and the other side is they won't play tennis. So if the humidity go beyond particular point, humidity and temperature related, the line is dependent on the temperature and humidity on that particular day. So on one side of the hyperplane, they do not play tennis, on the other side, they play tennis. So we are first interested in looking at linear support vector machines. So which we already seen. The two independent variables and hyperplane splits into two halves the response variable. Okay, yi is minus 1 and plus 1. This is minus 1, this is plus 1. Okay, and see that the two classes. Again is one class, that is another class. You can have any number of hyperplanes that separate both the classes. Okay, this diagram gives you three hyperplanes. They all separate the classes. Minus 1 is these green dots, and plus 1 is the red dots. Okay. Our aim is to find a hyperplane sin Wx plus b that correctly classifies our data. Isn't it? Always very interested in least errors. What are support vectors? Support vectors are those independent variables which lie on the hyperplane. The vector points closest to the hyperplane are known as support vector points because only those two points, it's only lying on the hyperplane, which are closer to the hyperplane. The vector points closest to the hyperplane are known as support vector points. Only these points are contributing to the result of the algorithm. We don't care about other points. So these points which are closer to the hyperplane, they're very important. If they shift, then your margin reduces. If a data point is a support vector, removing it has no effect on the model. Our goal is to maximize the distance between the nearest data point of either class and hyperplane will help us to decide the right hyperplane. The distance is called margin. See, so if this is the margin, but this and this, okay, this is the margin. So our aim is to maximize the margin. Of course, you can't make it too large also. So the one class is y is equal to plus 1, and another class is y is equal to minus 1. Okay, and d plus is the shortest distance, the closest positive point, and d minus is the closest distance, the shortest distance to the closest negative point. The margin is d plus and d minus. So the whole thing d plus d minus is the equivalent to the margin. So we have to maximize the margin. That is the goal of support vector machine. We want to classify a big margin, as big a margin as possible. That's the goal. Okay. So lots of possible solutions for. Suppose we take this line ax plus by minus c is equal to 0. There are lots of possible solutions for a, b, and c. Support vector machine finds the optimal solution. It maximizes the distance between the hyperplane and the difficult points, that is support vectors, close to the decision boundary. Which is the decision boundary? Each hyperplane is the from that to the nearest support vector is the decision boundary. If there are no points near the decision surface, then there is no uncertain classification decisions. SVM maximizes the margin around the separating hyperplanes. The decision function is fully specified by a subset of training samples. What are those? They are the support vectors. See, the support vector determine the decision function. Solving the SVM is a quadratic programming problem, seen by many as the most successful current text classification method. It is very useful for classifying text. So we are interested in building a maximum margin classifier with linear classifier. Okay. So the maximum margin classifier hyperplane, a natural choice is the maximum margin hyperplane, which is the separating hyperplane that is farthest from the training observation. It farthest from the support vectors. And then we can compute the perpendicular distance from each training observation to a given separating hyperplane. The smallest such distance is the minimal distance from the observation to the hyperplane and is known as the margin. The smaller distance, not the largest. Maximum margin hyperplane is the separating hyperplane for which the margin is the largest. You know that, right? That is the hyperplane that has the farthest minimum distance to the training observation. We can then classify that observation based on which side of the maximum margin hyperplane it lies. So new point comes, you place it, and from that you can find out which class it belongs to, whether you'll purchase a car or not. We hope that the classifier that is large maximum margin classifier on the training data will also have large margin on the test data, isn't it? See, it should be not apply only to the training data, but also the test data. So we want a good accuracy for both training phase and testing data. The same figure. So there is something called soft margin classification. That's important, you should know that. If the training data is not linearly separable, slack variables epsilon I can be added to allow misclassification of difficult or noisy examples. See here, this is all blue sphere. You allow this blue dot this side, and you allow the red dot this side. So they are called, you're asking slack variable epsilon I. The epsilon I, the distance of the epsilon I, can be added to allow misclassification. You allow misclassification to some extent. Allow for some errors. Let some points be moved to where they belong to at a cost. Still try to minimize training set of errors and place hyperplane far from each class. Still, although there are errors, still the margin should be high. The margin is not affected by misclassified data points. So soft margin classification is you allowing for errors. So the equation becomes pi w is equal to half w transpose w into c sigma epsilon I. So when you're minimizing it, you have to add this error component. Parameter c can be viewed as a way to control overfitting. Okay, this is all about the linear classifiers. Now let us do the implementation of support vector machine as a linear classifier. Okay. So what we do, we have to import libraries. This was the linear kernel. We call kernel. You will understand kernel in the next lesson. The linear classifier basically import these three, and we are taking social network adds data, and I'm printing the heads. That is the top 5 points. So I'm taking 2 and 3. If you look at 2 and 3, 2 is the pay and age and salary, and 4 is the whether he purchased or not, whether the customer purchased the car or not. So 0 means he did buy, 1 indicates he bought it. So you have to do the feature scaling. Always better to do feature scaling. Then after that, you split the data set into training and test data set. So there are 400 points. 320 goes to X10. X test is 80. So similarly, Y10, Y test. So I have also printed X test. So now we go to SVM classifier. From sklearn SVM, import SVC, that is SVM classifier. From sklearn metrics, import accuracy score because we want to find accuracy. So create a SVM classifier object. And the classifier is equal to SVC, kernel is equal to linear, random state is equal to 0. So here we are building a linear classifier. So train the classifier using training data, classifier.fit, xtrain, ytrain. Make the predictions, y predictions will classifier.predict, x test. Y test, y prediction, we can get for those test data by using classifier.predict. Classify the object of SVC. Now the accuracy score straight away you can get. Accuracy score y test minus y predict. You can print the accuracy also. So let us do this. Yeah, got it. So 0.9125 the accuracy, and it has done the classification of two classes. One is those who will buy the car or those who will not buy the car. You can also plot it. Of course, since the points are money, it's all, you can't make out anything. So for that purpose, I will plot a few points, actual versus predicted. This is how it looks. So if only red is there, that means actual and predicted are coinciding, merging. You can also find out the confusion matrix. It tells you the accuracy, can give you the accuracy of the algorithm. So run it. So you add 57 plus 16, 73 divided by 80. So that gives you accuracy is 91.25% or 0.9125. Okay. Understood? What we have, I will recapitulate once. You import libraries. Okay. Then you take the data set. Then you assign the data set X and Y values. Do feature scaling. Split data set into training set and test set. And then you can do the classification, and also you can find the accuracy. So that's all for now. Until we meet again. Bye bye.